Okay, next video. Exponential functions are continuous where the expression that represents the exponent is continuous. Recall a function in the form f of x equal a to the x, where a is greater than 0 and a is not 1, is called an exponential function with base a. Note the form here, we have a positive constant, not 1, raised to a variable exponent. So that's an exponential function. Then working towards an exponential function we'll see over and over and over again. Consider f of x equal 1 plus 1 over x to the x. And if we make a table of values for increasingly large values of x, we get this. And this number over here, where it doesn't keep getting bigger and bigger and bigger, it slows down. That number is called e. And so the chart above implies that the limit as x goes to infinity of 1 over 1 plus x to the x equals e. Now you do not have to remember how we came up with that number e. What you do need to remember is this. Know this. E is a number. Like pi, e is irrational, meaning its decimal approximation continues forever without repetition. E is approximately equal to 2.718. It is very important to remember that e is a number. The function f of x equal e to the x is called the natural exponential function. So e is going to creep up a lot. So determine where the following is continuous. And so our rule that we have up at the top there, an exponential function, that's an exponential function, are continuous where the expression that represents the exponent is continuous. So this will be continuous where the square root of 9 minus 6x is continuous. That's an even root. So it's going to be continuous where 9 minus 6x is greater than 0. And again, there's some debate whether you should put the or equal to or not. I don't care. Whichever. And so that's negative 6x is greater than negative 9, x less than 9/6, x less than 3/2. And so we conclude that it's continuous for x less than 3/2 or negative infinity to 3/2. And there's that one. Okay, next one. And we're going to run out of rules here soon. Rule 7. If the functions f and g are continuous at x equals c, then the following combinations are continuous at x equals c. F plus g, f minus g, fg, f divided by g, provided that g of c is not 0. F to the rs, provided that r over s is defined on an open interval containing c, and r and s are integers. So all that first part there, or all that second part, is just basically saying, making sure that you avoid imaginary numbers, blah, blah, blah. So rule 7 there is basically saying that if you're continuous at a number, then pretty much whatever you do to the function, if two functions are continuous at a number, pretty much whatever way you combine those two functions, still going to be continuous. The continuity is preserved through adding, subtracting, multiplying, dividing, and exponentiation, and square roots and that sort of thing. 9 or 8, we'll just accept this as a fact. The absolute value function is continuous for all reals. 9, if f is continuous at c and g is continuous at f of c, then g of f is continuous at c. And so this is just saying that continuity is preserved through composition. So determine where the following are continuous. And so, going into more detail than I'd expect of you from here. 3x, polynomial. Well, actually, let's put it this way. 3x, 2x, polynomials, continuous everywhere. cosine, continuous, everywhere. Continuous, everywhere. So cosine 2x, composition of two continuous functions, so continuous everywhere. Remember composition, the idea of putting a function inside a function, and continuity is preserved through composition. Then finally, 3x plus cosine 2x, sum of two continuous functions, so continuous everywhere, or negative infinity to infinity. And so there's kind of the logic what we'll be doing on this one, just noting that each part was continuous everywhere, and then when we put all those parts together, still continuous everywhere. Next one. Determine where the following is continuous. Okay, logic here. 3x, continuous everywhere. Again, because it's polynomial. 2 sine x plus 1, continuous everywhere. Same logic that we had before. Sine x is continuous everywhere. When I multiply it by 2, add 1, still continuous everywhere. But now it's a fraction. But as a fraction, it's going to be continuous, or let's put it this way. Discontinuous, where 2 sine x plus 1 equals 0. And again, the reason why when we're dealing with fractions that we have discontinuities where the denominator is 0 is because division by 0 is undefined. And for continuity, you need things to be defined. So solving this trig equation, remember the first step in solving a trig equation is to solve for the trig function. So sine x equals negative 1/2. Then I ask myself, where is sine equal to 1/2? In radians. So there's a little unit circle. And sine x equals negative 1/2 at, it equals 1/2 at pi over 6, but that's positive 1/2, so I need the negative. And so sine is negative in the second and third quadrants. I just may have confused myself. Sine is negative. I said second and third quadrants. That's wrong. Sine is your y-coordinate on the unit circle. Your y-coordinates are negative in the third and fourth quadrants. So sine is negative at 7 pi over 6 and 11 pi over 6. And so I would be happy pretty much with that answer. If you wrote discontinuous on those guys, I would be happy with that answer. Give me the primary unit circle values. But the perfect answer, so there's approximately 7 pi over 6, and there's approximately 11 pi over 6. Perfect answer would be, if I'm going to answer the continuity question, continuous for all reals except 7 pi over 6 plus 2k pi and 11 pi over 6 plus 2k pi. Now you're looking at that 2k pi thing, or maybe you'll see 2n pi, and what the hell is that? That is picking up all the possible unit circle answers. Remember how the unit circle works. You can just keep going around and around and around. So 11 pi over 6 is one answer, but if I go around the unit circle and hit it again, that's another answer. I go around the unit circle again, or if I go backwards around the unit circle. So the way you pick up all the answers is to throw on that plus 2k pi, where k represents an integer. Now, I will always be happy and tickled pink if I get the primary unit circle values. But in my math lab, every once in a while, they're going to ask for this. And the way you get all the possible angles is to add on 2k pi. Now sometimes there's ways you can get all of them by not doing each angle separately, but when in doubt, if you're trying to get all the angles, do each angle separately and add on the 2k pi. That's just circling around and around and around the unit circle. Good place to end this video.